Hey, it's Mr. Clausen here. I've been getting some questions on how to calculate momentum using the conservation of momentum, and yeah, it can be kind of tricky because there's a lot of things to overwhelm you. But if you can multiply two numbers, which is to calculate momentum, and you can add numbers together, which is how you add things up to find the total, you can use the conservation of momentum to solve problems as long as you show your work along the way. So let's just take a look at it. The first thing to note here is the law of conservation of momentum. What is it? Law of conservation of momentum says that the total momentum of an isolated system is going to remain constant. And what that means is for something to be an isolated system is there can't be any other forces acting on it. So if like a car driving down the road is not an isolated system because you're pushing on the gas pedal, which is using more energy and adding energy to the system. To get the car moving. So that wouldn't be. What we're really talking about here is just that moment when two things interact, like two billiards balls hitting. I think the lesson on our website talks about marbles. Or a good example, which I often use for this one, is this little thing here. It's called a Newton's cradle. Now, it works just for a moment. At that moment of collision, I'm going to bring this over just a smidge more. And actually, we can make this picture bigger so you can see. All right, so there we go. Let's do this. There we go. So we call this a Newton's cradle, and how it can do it is it can show the conservation of momentum. If you take one sphere, right? So I have one sphere here, I pull it back, I let it go. It's going to be moving with a certain amount of mass. It has a certain mass, it's moving with a certain velocity. And you'll notice before the collision, there was only one sphere moving, and after the collision, there's one sphere moving. Now, it's not 100% perfect because nothing can truly be an isolated system 100%. There's always ways for energy and stuff to get in and out. Like you can hear the little clickety clack. So it's losing a little bit. But we can still use it to solve for the most part. All right, so if I do this again, one sphere in, one sphere out. So there was one sphere's worth of momentum coming into the collision, and then there is one sphere's worth of momentum coming out. One sphere of mass at that speed, and you'll notice that the speed is the same going in and out. Now, we can do more than just one. Okay, what if we do two? Well, if we had two spheres coming in, we should get two spheres coming out. I bumped it a little. All right, let's get it settled down. Let's do three. Okay, three spheres in, three spheres out. We're gonna go up to, don't worry, we'll do them all. Okay, four in, four out. So you can see at any one time, there's only four spheres moving. There we go. And then there's always one student that asks me, can you do five? Do five. And so that's for you if we do all five. So five spheres in, five spheres out. Okay. Another way to take a look at this is it doesn't have to be just one way. We could do two and one. So if we do that, at any one point, there's only one sphere coming in and two spheres the other direction. All right. So conservation of momentum, big idea. However many spheres are coming in, that's how many spheres are going to come out because it's the same mass and their velocity. All right, we'll put that off to the side, and then let's take a look at how to actually solve these problems. Okay. Hopefully this is going to work for me. So to get the total momentum before something and total momentum after, all you have to do is we write that down in science. We say momentum, which is the Greek letter rho, or it looks like P, and then we put a little subscript on it that stands for total. So a little subscript T standing for total. So the momentum before has to equal the momentum after. But if you take a look at this, you're like, wait, how can I tell which one's which? It's the same symbol. We put a little Greek, or put that little apostrophe up there that stands for prime, and it just means after something happens. So the way you'd read this mathematically is momentum before equals the total momentum after. All right. Now, in our little example, though, how would you find the total momentum? Well, there's 5 different spheres. So A, B, C, D, E. You'd find the momentum of sphere A. You'd add it to the momentum of sphere B, add that to the momentum of sphere C, and you continue on for as many objects as there are. So then how do you figure out the momentum after, on the second half there? You do the same thing. It's the momentum of sphere A prime plus the momentum of sphere B prime plus the momentum of sphere C prime for as many as there are. And remember, prime just means after the collision happens. All right. So you're like, okay, not so bad. Just find the individual momentums, whatever. But then it can get more confusing because momentum is mass times velocity. And so if you're looking for just one equation for this, it ends up being this just like big long thing because you'd have to do massive moment or massive object A times velocity of object A plus massive object B plus times velocity of object B, mass times object C. And really all you're doing there is you're just calculating the momentum of each object and you're going to add them all up. And then you would do the same thing for that. So when you're doing your problems here, yes, there is one equation we could do to figure out what is the final velocity. But it's such a big equation going on there that it tends to like you put something in the wrong spot and the whole thing falls apart. So I think it's just a little bit better if you break it apart and just do it object by object. And I'll show you what I mean by that. And so once again, if you take a look at this, is there really anything here that isn't just multiplying or adding together? Mass times velocity. Plus. Okay, so that's what's going on there. So let's take a look here. Let's say you got an example problem. What I want us to do is you're on a skateboard or a kid's on a skateboard. They have a mass of 55 kilograms and they're just sitting still, and somebody throws a medicine ball at them. All right, so those little lines there are supposed to be my showing that it's moving. It has a mass of 4 kilograms and it's moving at 15 meters per second. All right, now the medicine ball hits the kid. The kid does some sort of like ninja punch or something and punches the ball straight back. So the ball's now going the other direction and the kid goes flying backwards because of it. The question would be, how fast is the kid moving after the collision? So what I've done here to help solve the problem is I drew a picture of both before it happens and after it happens. And then the other thing I did is I labeled all of the stuff for before and after. If you try to just go through and put these all in, like you totally could, by the way, use this bottom equation right there. And like this, here is the mass of the kid. Here's the momentum of the ball. Add that together. There's the mass of the ball, and then there's the mass of the kid. You could rearrange that and solve for V prime, and it would work. I just think it's much easier if you just solve for their individual momentums. So let's just remember how to calculate momentum. Momentum is equal to mass times velocity. So what we want to do is find the momentum of the ball, find the momentum of the kid, find the momentum of the ball after. Oops, I realized I didn't put my primes on that one. Okay. And what will help us out is if we found the momentum of the kid after, we would be able to figure out the velocity. Now, just run with me on this. The momentum of the kid afterwards would be equal to the mass of the kid times the velocity of the kid, right? Now, this question is really starting with this idea right here. How fast is the kid moving after the collision? And so this is what we're trying to find, right? Now, we know this, right? We know the mass of the kid. So if we knew the momentum of the kid after, we would be able to figure out the velocity of the kid. So let's just go through and calculate all their momentums. It'll go pretty quickly. If you got your calculator, you might even already be done with it. So let's just do the first one. The first one would be 4 times 15. All right. So it's 4 kilograms times 15 meters per second, meaning the momentum of the ball before is equal to 60 kilograms times meters per second. Okay. The momentum of the kid beforehand, he would be 55 times 0, giving him a momentum of 0, which makes sense. Momentum is how difficult it is to stop a moving object. So if you're not moving, you have no momentum. So we got that. So what I'm going to help you out here is, what is the total momentum to begin with? Well, you just add those two together, and it's not too hard to figure out that 60 plus 0 is momentum total. I'm actually going to write it over here. Yeah, it's just right here. Momentum total is 60 kilograms times meters per second. Sorry, I'm getting ahead of myself. It's not meters per second squared yet. We're not dealing with acceleration. All right, so we got that part. Let me just highlight what we did. Momentum of the ball, momentum of the kid. We added those together. The total momentum before the collision is 60. All right, let's start figuring out what's going on the second half. What is the momentum of the ball after? So it's going to be 4 times negative 0.8. And if you run that into your calculator, you get that the momentum of the ball afterwards is, very good, negative 3.2 kilograms times meters per second. See what I did there? I paused and waited for you to say it, and I was just hoping you'd actually say it. I don't know if you really did. All right, so we got that. So how is this beneficial? Well, remember that the momentum before has to equal the momentum after. So what is the momentum after the collision? Well, it's also going to be 60. Okay. And that's going to be equal to the momentum of the ball after plus the momentum of the kid after. You still with me, I hope? We now know this. We just calculated this, which goes there. And if we find this, the momentum of the kid, we can put that up there and then finally find the velocity. All right, so let's go ahead and solve for the momentum of the kid. I'm just scrolling down so I have a little bit more room. Let me highlight some of our answers that are going to be beneficial. So what I'm going to do now is take the momentum of the ball and I'm going to plug it in right there. So let's write out what that would be. We would have 60 equals negative 3.2 plus the momentum of the kid after. All right. To solve for the momentum of the kid, we just add 3.2 to both sides. And so the momentum of the kid after the collision is going to be equal to 63.2 kilograms times meters per second. Now, why is that beneficial? Remember, the whole point of this problem was to figure out the velocity of the kid after the collision. And we know the mass of the kid, and the only thing that was holding us up is we didn't know this value right here. But we just calculated it down here on the bottom. It's 63, so we can use that to help us out. So let's find the velocity of the kid after the collision. Momentum of kid after is going to be equal to mass of kid after times velocity of kid after. I just rewrote it so that you knew what I was doing with, and then we can plug our numbers in where they belong. This 63 can go over here. The mass of the kid is still the 55. That didn't change. And the only thing left we have to find is this value right here. That's our unknown. That's the velocity of the kid. To solve for that, we divide both sides by 55. I don't know what I got here. I got some work from a previous problem. And if you take 63.2 and divide it by 55, you will get a velocity of 1.15 meters per second. Okay. All right, so I know that's a lot of steps. Let me run just back through it with you. But each step isn't very difficult if you look at just the step itself. So let's go back to the beginning. We've got a whole bunch of different objects, right? Each object has its own momentum, right? So right there and right there. So we got the 4 different things we're taking a look at. Each one has its own momentum. In the beginning, if you take their 2 individual momentums and you add them together, you get the total momentum before something happens. We know from the law of conservation of momentum that that momentum has to be the same for after. Well, afterwards, it's just the momentum of the 2 objects added together. The momentum of the ball, which is easy to calculate, and the momentum of the kid. And the reason we're using the momentum of the kid is because it's going to tell us what the velocity is afterwards. Okay, so what we did is we took the momentum before and the momentum after. We said they were equal. We used the momentum of the ball after, and we figured out what the momentum of the kid must have had afterwards. Once we knew that, we used his mass, and we were able to solve for the velocity of the kid. Okay, so there's that. I hope this helps out a little bit. These are complicated problems. Like this is a very complicated problem. In physics, this is one of the harder ones we would do in the courses because it is multiple step. You will see that each step isn't hard because in this one, how do you actually do it? Well, you just take, I mean, literally it's 4 times 15. That's not a hard step to do. In this step, this isn't a hard step because you just add 60 and 0. That's not a hard step either. But the process is just knowing how it all goes together, okay? And I think the big idea is that whatever the total is here, so if you find their momentums and you add them all up, that has to be equal to all their momentums over here. And because of that, you can then use that to find individual momentums. I really do hope this was helpful. Please reach out to me with questions, and we'll talk to you guys later. Bye.